Good evening. We are Team Tech Titans from MMIT, and we are here to present our project SmartSenseCNC, a real-time CNC the machine downtime detection system built using the Myosa IoT kit. So, here's the problem. Most CNC machines in SME workshops sit idle for hours, and nobody even notices. The machine is on, the power is being consumed, but there's no real work done. Most workshops still rely on manual observations, which is highly inconsistent and highly unscalable. Our studies show that 37% of capacity is lost due to these downtime, and which is approximately like 2 hours per shift. For most small-scale manufacturers operating on thin margins, this silently kills their profit.
So we're from MIT College, and the problem statement we've identified is that there are many CNC machines in industries where downtime isn't calculated. So could you please tell us about any such problems you've faced in your specific industries?
Our downtime, we just do it manually. Downtime is monitored, but it's done manually. We don't have any major technology for that yet. Okay, so mainly our downtimes are mostly maintenance related, like sensors constantly toggling, the spindle motor cycling, or persistent clamping issues, right? Or issues like material getting stuck.
We're from college and we've just identified a problem. We wanted to ask you about it. So basically, we've identified that downtime isn't being accounted for in CNC machines. So are you facing any problems like that related to downtime?
We're facing issues like that. So tool life monitoring says it took 15 or 20 minutes to change a tool, but we don't know the actual lost time. Production claims 15, tooling says 20. That's a problem. If an operator takes a tea break, the machine stops, and we don't know how long it's been idle. We need a solution to track downtime.
So here is our solution, SmartSenseCNC, an IoT-based real-time CNC machine monitoring system powered by Myosa ESP32 board. It detects machine state intelligently, gives alert, and analyzes downtime automatically. It has mainly 3 steps. First is off step, where the machine is off and there are no tasks or jobs. Second, ideal step, where the machine is on but there are no jobs, which leads to downtime. Here, downtime alerts get triggered. Next, we have active state, where the machine is on and there are jobs. Here, production time gets recorded. Our system does this all using multi-sensor fusion. We get live updates on dashboard. Then we have used non-invasive current sensors, which requires 0 machine rewiring. And last, we have used random forest classifier with 92% accuracy. So here is hardware and software stack. On hardware side, we have ESP32 Myosa board for main processing, then MPU6050 as a vibration sensor, then SCT013 and ADS1115 as a non-invasive current sensors, and last OLD and buzzer for alerts. Our software mainly runs on Arduino firmware. Then Python Flask is used as a backend. Communication protocols like POST, scikit-learn for random forest, and SQLite as a database, and Chart.js dashboard for real-time updates or analytics. Then why we have used machine learning instead of fixed logic here. A traditional rule-based logic works as if current is greater than 5 ampere, then machine is on. But it only works for one machine. Then it needs manual calibration. Then it is poor for scalability. Different CNC machines have different patterns like noise or vibration. On the other hand, we have machine learning model which learns directly from data. It gives better accuracy. It reduces false alerts, then handles machine vibration automatically. Easy deployment across workshop, and it is also Industry 4.0 ready. Next, my teammate Vedika will continue.
Now let's understand the end-to-end system workflow. It consists of 6 basic steps. Firstly, the sensor data collection, where the vibration and the current is collected. Next, the ESP32, which computes the RMS values, and the data is then sent via HTTP post. Now, the random forest model predicts whether the machine is off, idle, or it is working, and it logs with a particular timestamp. Now, the dashboard updates in every 5 seconds. And if the idle state is detected, the OLED and the buzzer sends the alerts accordingly. The downtime trends are visualized on the dashboard. Next, we have the machine learning classification engine. Here, the engine accepts 2 input features, that is vibration RMS from MPU6050 and the current RMS from the SCT013. The random forest classifier that is ensemble of decision trees, and it is trained on labeled CNC operational data. It is very robust to noise and also runs on fast inference. Now, the state cycle keeps updating in every 2 seconds. Now, let's understand the impact, advantages, and the future roadmap. The results speak for itself. About 40% downtime reduction is observed for hidden idle losses recovered per shift through real-time alerts. And the energy savings is done about 23% via automated monitoring. We have the future roadmap, that is cloud analytics platforms, that is multi-plant monitoring, predictive maintenance using trend models, and mobile app scaled to entire workshop flows with smart mobile phone access. The SmartSenseCNC is an affordable Industry 4.0 intelligence for every SME workshop. Thank you.